Question 12 from section 1 of the 2017 Higher Physics Examination from the SQA. A ray of red light passes from a liquid to a transparent solid. The solid and the liquid have the same refractive index for this light. Which row in the table shows what happens to the speed and wavelength of the light as it passes from the liquid into the solid? Now, to help us find out what's going to happen to the wavelength and the speed, let's go to the PHET physics simulation site and see what happens. Okay, here we go. This is a website where you just must go and practice your physics. So here we have on the top of this line here, this line is the interface between the liquid and the transparent solid. You can see we have the normal, and we've got little laser beam here. We're going to fire off a red light towards the normal in about a second. Above the border line here is going to be the liquid, and below the border interface is going to be the transparent solid. So let's fire up the laser, and there's the red light passing right the way through that normal from the liquid into the transparent solid, and you can see the ray has been unchanged. Even if I change the angle with the normal, you can see the ray of light is unchanged when it enters into the transparent solid. Let's take a look at the wavelength of the red lights, and as you can see, the wavelength is the same in the liquid as it is in the transparent solid. Even if I move the angle, you can see there's going to be no change between the liquid and the transparent solid for the wavelength. And this is because the liquid and the transparent solid have the same refractive index. Now, what about the speed? Well, we use our speed counter here. You can see the speed is 0.67 c. That means it's 0.67 of the speed of light, 3 times 10 to the power 8 meters per second. And if I bring the speed measurement into the transparent solid, that's below the line, you can see there's no change in speed either. So what we've ascertained is that when you have two mediums which have the same refractive index for that particular wavelength of light or colour of light, in this case we've got liquid and transparent solid, both with the same refractive index, there will be no change to the speed, there will be no change to wavelength, and there will be no change to the direction. So we can go back to our question and see what answer we're going to choose. So speed, no change, and wavelength, no change. So our answer is definitely going to be answer E. Question 13 from section 1 of the 2017 Higher Physics Examination from the SQA. A ray of blue light passes from air into a transparent block as shown. And we're asked to find the speed of this light in the block, and we're given our 5 responses. So if we look closely at the block, you can see it's dealing with the angles, and we've got to find an equation from our data sheet which links up angles and speed. So we go towards our higher relationship sheets, and you can see we're going to use the 4th expression down that list, because we've got sine theta 1 divided by sine theta 2 equals lambda 1 divided by lambda 2 equals v1 divided by v2. Now, we're not interested in the wavelength because we're not asked to find that, so what we'll write down is sine theta 1 over sine theta 2 is equal to v1 over v2, and that's the one we're going to use. So changing the subscripts a little bit to suit our problem, we have sine theta in the air, always start with the air first, sine theta in the air divided by sine theta in the block, that's the block angle, is going to equal to the speed of light in the air divided by the speed of light in the block. So we can put in our numbers for this then. We can say that sine, and it's going to be theta in the air, is going to be 60 degrees. It's always between the normal and the ray of light, divided by sine theta in the block, which is going to be 40 degrees, because it's always between the ray and the normal. That equals the speed of light in the air, which we take to be 3 times 10 to the power 8 meters per second. And we divide that by VB, and VB is what we're after, the speed of light in the block. So if we actually do sine 60 over sine 40, we're left with an answer about 1.35. No units, it's dimensionless. and that's going to equal to 3 times 10 to the power 8 divided by VB. A bit of algebra moving about now. We cross multiply and we get 1.35 times VB on one side, and that's going to equal to 3 times 10 to the power 8 on the other. And finally, to get VB on its own, we must perform the division of both sides by 1.35. So it's 3 times 10 to the power 8 divided by 1.35. Okay, we do that in our calculator and we end up with the speed of light VB comes out to be about 2.22222, which we'll write down. The closest answer we can get is 2.23. So 2.23 times 10 to the power 8 meters per second will be the speed of light in that block. And that's going to give us an answer to this question of answer D, 2.23 times 10 to the power 8 meters per second. Question 14 from section 1 of the 2017 Higher Physics Examination from the SQA. A student carries out an experiment to investigate how irradiance varies with distance. A small lamp is placed at a distance d away from a light meter, and the irradiance I at this distance is displayed on the meter. This measurement is repeated for a range of different distances, and the student uses these results to produce the graph shown. Now we look at the graph, we can see the x-axis is 1 upon d squared and the y-axis is the irradiance, and it's not passing through 0. We know that the rule for irradiance is the following. We know that the irradiance I should be borne out in experiment to be proportional to 1 upon d squared, which means that we should have a graph like this. If we plot 1 upon d squared, and that's the irradiance, then that condition will only hold if it's a straight line passing through the origin. Now it's plain to see from the graph that the student has obtained that that line's not passing through the origin. Now let's take a look and see why that's the case. Now as we go towards, as we go further and further away from the light source, 1 upon d squared is going to go towards 0. So we're going to come down here. Now if that was the case, we should be detecting less and less light, because the irradiance from the little light bulb is actually being put over a bigger area. So that should be down towards here, but the very fact when we look at the student's graph, we are seeing that we're gaining some irradiance, even very far away from the light source. So it's something to do with the ambient light, and that's the clue we're going to look at. Now if you look through all the different questions here, different responses, part A, repeating the readings and calculating mean values, now that's not going to reduce the systematic error, which is an error involved in the actual experimental setup. Replacing a small lamp with a large lamp, well, that will totally destroy your irradiance is directly proportional to 1 upon d squared, because that only works for a point source of light. So if you make the bulb bigger, it will not give you the straight line. So we can rule that one out. Decreasing the brightness of the lamp, that will be in every result, and it will just give you the same sort of kind of graph as this. Repeating the experiment in a darkened room, gotcha. That's the one we actually use, because if the room has got some light leaking into it, then even if we take our detector further away from the light source, we'll still be picking up the ambient surrounding light. So that will be the main one, number D. What about E, increasing the range of distances? Well, that's just going to extend your graph further and give you more data. It won't actually rule out the systematic error. Remember, a systematic error or uncertainty is due to something that's wrong with your experiment. So in this case, it's to do with the experiment not being done in a darkened room. So our answer to number 14 is going to be D. Repeat the experiment in a darkened room.